All right, let's get right into it because something truly wild has happened in the world of quantum computing. For years, the story was always the same. A useful quantum computer? Oh, that's decades away. A problem for the future. Well, guess what? The future is showing up way ahead of schedule. That timeline has suddenly, and I mean dramatically, shortened. And no, this isn't just hype. We're hearing top researchers, the people actually building these things, use phrases like vibe shift. I love this quote from Natalie DeLeon at Princeton because it just nails it. The whole mood in the community has gone from this, cautious, long-term skepticism to a real, genuine, this is happening kind of optimism. So what on earth caused this huge shift?
Just look at this timeline. It really shows you the insane acceleration we're talking about. A few years back, several decades. That was the standard answer. Today, people are seriously talking about a 10-year window for machines that can solve real-world problems. Computer scientist Dorit Aharonov says we've entered a completely new era. This isn't just a small step forward. It's a huge leap. But to get why it's happening now, we've got to look at the monster problem that was holding everything back.
And that brings us to the absolute core of the challenge, the Achilles heel of quantum computing, the error problem. To really appreciate the breakthrough we're about to talk about, you have to understand the sheer scale of this barrier. This one single issue is what made building these machines seem almost impossible for so long. Okay, so it all starts with a qubit. This is the fundamental building block. Now, think of a regular bit in your laptop. It's like a light switch. Simple. It is either on or it's off, a 1 or a 0. A qubit, though, a qubit is more like a spinning top. It can be pointing up for 1, down for 0, but it can also be in this weird, fuzzy superposition of all the other angles in between, all at the same time. And that's where all its incredible power comes from. The difference is just night and day. A classical bit gives you a simple choice. A qubit gives you an entire sphere of possibilities to work with. That incredible complexity is what lets a quantum computer tackle problems that would take a normal computer billions of years. But, and this is the big but, that complexity is also its greatest weakness. It makes them unbelievably fragile. For decades, there were these two killer problems. First, these delicate quantum states, they just don't like to sit still. They naturally drift, they decay, they lose the information they're holding in a fraction of a second. It's like trying to write on water. And second, the very act of using them, performing operations or gates, and then measuring the result, that process itself introduces even more errors. So how in the world do you build a reliable computer out of parts that are just constantly failing? Well, that brings us to the solution, the incredible breakthrough that completely changed the game and kicked off that vibe shift. Scientists have finally figured out a way to tame the quantum world. This is the central question, right? The one that kept physicists up at night for years. If your basic parts are constantly messing up, how can you ever trust the answer to a complex calculation? Turns out the answer isn't about building one perfect qubit. It's about being incredibly clever with the imperfect ones we already have. And that clever answer is a technique called quantum error correction, or QEC. The basic idea is just brilliant. Instead of trusting one fragile physical qubit, you take the information of one stable logical qubit and you spread it out across a whole team of physical ones. These physical qubits then act like a support system, constantly checking on each other, spotting errors, and correcting them on the fly before they can wreck the whole computation. And here's the real kicker. This is not just a theory anymore. We have hit a watershed moment. In just the past year or so, 4 different incredible teams, Google, Quantinuum, Harvard, and USTC in China, all independently proved that this actually works. Using totally different technologies, from superconducting loops to trapped dynams, they all demonstrated they could lower the error rate below a critical point. This was the proof of concept everyone had been waiting for. It meant for the very first time that building a big, fault-tolerant quantum computer was a real engineering project, not just a physicist's dream. But as it always goes in science, right? You conquer one massive mountain, and from the top, you just see the next, even bigger one. Proving error correction works opened the door to a brand new massive engineering challenge, the overhead problem. So what exactly is this overhead? It's just the number of physical qubits you need, that whole support team, to create one single, stable, logical qubit that you can actually use for a calculation. And at first, that support team had to be enormous. The early numbers were, well, they were daunting. You'd need something like 1,000 physical qubits just to create one useful logical qubit. 1,000 to 1. Now just think about that. If you need, say, a few thousand logical qubits to solve a really interesting problem, you're suddenly talking about building a machine with millions of physical parts. The engineering scale was just astronomical. But here's where it gets really exciting. Thanks to some incredible innovation, that number is coming down fast. The new target that researchers are aiming for is an overhead of around 100 to 1. That's a tenfold improvement. And that right there makes building a powerful quantum computer feel so much more achievable.
So, the name of the game right now, the thing everyone is focused on, is efficiency. The entire field is now in a race to shrink that overhead to make these error correction systems as lean and mean as possible. This is the direct path to a machine that can actually do something useful.
And they're not just hoping for the best. There's a clear strategy. It's like a three-pronged attack. First, you write smarter algorithms that just don't need as many qubits to begin with. Second, you invent better, more efficient error correction codes. And third, you go right back to the source and you build fundamentally stronger, better physical qubits that don't make as many mistakes in the first place.
And we're seeing huge progress on all fronts. Just take that third one, stronger qubits. Natalie DeLeon's team at Princeton found that by switching a material they used from aluminum to something called tantalum, they boosted their qubits lifetime from 0.1 milliseconds to over 1.6. I know that doesn't sound like a lot of time, but in the quantum world, that's a massive leap in stability. And they think they can push it to 10 milliseconds or more. A longer life means fewer errors, which means you need less overhead for correction. See how it all connects? So the bottom line is, this isn't just guesswork anymore. Researchers have clear, concrete goals. I mean, listen to Harvard physicist Mikhail Lukin. He says his team is well on the path to 3 nines. That's just jargon for 99.9% accuracy on their quantum operations. A few years ago, that level of precision was almost unthinkable. Now it's a real engineering target that's actually within reach. So all of this progress, this vibe shift, the shrinking timeline, the engineering breakthroughs, it all brings us to one final huge question. For the first time, the path to a large-scale working quantum computer is actually clear. So the question is no longer if these machines are going to work. The real question is, what will they do first? With this accelerating pace, what currently unsolvable problem in medicine, materials, or even code breaking is going to be the very first to fall?